Hi, I'm Dr. S and this is video 7 in my series on reaction rates for Year 13 A-Level Chemistry. This video is about initial rates. By initial rates I mean the rate at time equals 0 as soon as you mix reagents together. Now the whole purpose of the experiments I'm going to explain is to look at the link between concentration and rate. So effectively what I want to be working out in the end is a rate concentration graph. How does the rate change as the concentration of a reagent changes? So far with what we've looked at are concentration time graphs. So we're going to look at how concentration changes as time changes. Now we can calculate the initial rate from a concentration time graph by taking a tangent at time equals 0 and we'll work out the actual rate. But the problem is if we want a rate concentration graph, we would have to do this graph 4 or 5 times, which would be time consuming. There are quicker and more convenient ways of doing it, which are known as initial rates methods. So these rely on reactions that allow you to observe something and then see how fast that happens. But it has to be quite a quick change. So a common example of a reaction that you will have done this with is what we call the disappearing cross. So if you remember the disappearing cross experiment, we mix together sodium thiosulfate plus hydrochloric acid, and it makes sulfur, which is a precipitate. It also makes sodium chloride and some water and SO2, but it's the sulfur that's important. And if you remember what we do with this, we have a conical flask with a solution in it, and underneath that conical flask we have a piece of paper with an X on it. Now if you imagine looking at that from above, conical flask with the X, and you can see the X through the conical flask. As the reaction proceeds, the sulfur is formed, which turns the solution into a suspension. That suspension you cannot see through, so you can no longer see the X. If you imagine looking at it from above, there's the conical flask with the X on it. The sulfur has been produced so that the X has been obscured. So what we do is we mix chemicals together and we take the time it takes for the X to no longer be visible. And what we can do is we can change the concentration of thiosulfate, for example, and see how that affects the time. That's a very common GCSE experiment. In fact, it's a required practical in a lot of exams now these days. So let's look at how we would use that and try and get a rate concentration graph from it. So I'm going to show you some example results from this experiment. So let's say that I changed the concentration of my thiosulfate ion, the sodium thiosulfate. And I had, so this is in moles per decimeter cubed. And I did 5 experiments, 0.3 mole per decimeter cubed, 0.24, 0.18, 0.12, 0.06. And I took my times that it took for the X to disappear, so time in seconds, and that was 11, 14, 18, 30, and 80. And as expected, as the concentration decreases, it takes longer for the precipitate to form and for the X to be obscured. Now the problem with this is if I now want to put this on a graph, what I have is concentration against time, and the graph's going to look like this. Now there's not much I can tell from a concentration time graph that way around. So what I need to do is translate the times into rates. Now what we can do is then calculate 1 over t in seconds to the minus 1. Time is inversely proportional to rate. The faster the rate, the shorter the time. If I do 1 over t, what we should start to see is that as I put my numbers on, it should now be a positive correlation between the concentration and 1 over t. as the concentration decreases, so does 1 over t. Sorry, there's a 0 there, 0 there. So you can now see that as the concentration decreases, 1 over t decreases. So if we now graph this, concentration 1 over t, actually what we get is a straight line. 1 over t is proportional to rate. These are not the values of the rate. You can calculate the value of the rate if you want. I'm not going to go into that now. But they are proportional to the rate. So the result would be the same. Now we do have to say this is only the situation in this case because this happens to be a first order reagent. But you should be able to see how by using initial rates methods like the disappearing cross and then calculating 1 over t for different concentrations, we can get a graph of 1 over t against concentration which is proportional to rate over concentration. So what we'd have is a straight line there. What I'll do in the next video is then look at how these graphs, the rate concentration graphs, would be different if it was a 0 order or a second order reagent. Okay, I'll see you then.